Welcome to this podcast. The subject is multiple rate of return values. It includes a summary of the tests that help detect multiple ROR values for any cash flow series, followed by an overview of two techniques that can remove multiple values and find one unique ROR value given specific conditions. There are two types of cash flow series, conventional and non-conventional. Conventional series have only one change in sign, usually from a negative amount in year 0. This initial amount represents the investment or first cost of the project. Then at some time after year 0, the cash flow turns positive and continues positive until the end of the expected life N. If the signs on cash flows change more than once, then the series is termed non-conventional. Herein lies the problem. The ROR computation can on occasion be misleading when the IR values are determined. Here are two example series. Look at series 1. As you can see, it has only one sign change in year 3. Now, take a look at series number 2. Note that the cash flows flip from minus in years 0 and 1 to positive in year 2, back to minus in year 3, and returning to positive in years 4 through 6. In all, there are a total of 3 sign changes. Multiple sign changes indicate the possibility of multiple I star values. These values may be positive or negative real numbers, including 0, and they may include imaginary or complex numbers. The exact nature of the roots to the polynomial equation used to find I star values is unknown at this point. There are two tests that concern cash flow sign changes that can help specify the number and nature of the I star values. The first of these tests is called the rule of signs. It is also known as Descartes' rule, which you are likely to have learned in your college algebra course. Actually, we just applied this rule on the previous slide. Simply count the number of sign changes. This puts a max on the situation in that it determines the maximum number of real number roots that may exist. The second test, which is slightly more definitive, is termed the cumulative cash flow sign test. It is also known as Nordstrom's criterion. It uses the number of sign changes in the cumulative series to determine if there is one unique positive I star value. If the cumulative series starts with a negative cash flow and has only one sign change, then there is only one positive I star value that can be found. However, there may be other roots to the equation. This is where the negative, the imaginary, and the complex roots may appear. Even though they may not be of any interest from the economic decision perspective, they can call into question the legitimacy of the one positive I star value. Here is an illustration of both tests. The cash flow series changes sign 3 times, here, here, and here. The right column shows the cumulative cash flow series starting with the value of minus 1,000. The second test is very helpful in this case since there is only one sign change in this cumulative series. The conclusion? There is only one positive I star value. Consider this cash flow series. We will apply the tests and use the IRR spreadsheet function to find the I star values. Initially, test 1 results in 2 sign changes to limit the potential ROR values to 2. The cumulative series that is shown here has one change in signs and starts with a value of minus 12,000. This is great. It means that there is only one positive I star value. However, as mentioned earlier, we must be aware that there may be other non-positive or non-real number roots. First, use the IRR function for the range of cells from B3 to B8, that is minus 12,000 to minus 5,000 in cash flow, and we get a value of I star equals 0%. Of course, this is correct, since the last of the cumulative series is 0. This indicates that the investment is recovered with no positive return. Are there other real number values that should be considered? Yes, there is another root. Let's reapply the IRR function, and this time use the optional guess operator. If we set guess to a negative value, like minus 50% as shown here, the other root appears. It is minus 56.37%. Now this result is of no economic significance compared to the return of 0, but we do still have two I star values. Mathematically, this calls the analysis into question.
A sound economic decision should be based on one realistic I star value. Multiple roots bring any economic decision into question. What should we do with multiple roots? Let's assume there are two real number roots. Here are some guidelines. If both I star values are negative, or both are positive, discard both of them and use one of the techniques that follows to obtain a unique I star. Alternatively, use a PW, FW, or AW analysis at the set MARR to make the economic decision. If there is one positive and one negative root, discard the negative and use the positive root, provided it is a realistic value. Even here, it is better to opt for a PW, FW, or AW analysis at the MARR to obtain a definitive result. To continue, we need to understand the complement of the IROR, that is the EROR, or external rate of return. Estimates outside or external to the cash flow series are specified, and these help in removing spurious I star values. However, it is important to understand that I star values different from the internal rate of return values will develop as these external estimates are applied. Here are two important rates. These are both outside the series itself. They are the reinvestment rate, I sub R, and the borrowing rate, I sub B. As shown here, I sub R is the expected rate on leftover cash, that is, excess money at the end of each year of the project. The MARR is commonly used as the reinvestment rate, I sub R. If borrowing is necessary, I sub B is the cost of money for outside funds. Two methods can be used depending upon the situation, and they are the MIRR approach and the ROIC approach. These will result in different I star values, but either method is guaranteed to provide a single real number value for I star. This rate is called the EROR, since rates external to the cash flow series are used in the analysis. Let's take a brief look at each method. The modified ROR, or MIRR approach, results in one of these unique I star rates. We will call this rate I prime. MIRR uses both external rates for reinvestment and the borrowing rate. For example, assume an MARR value of 9%, with I sub R and I sub B rates shown here. There is a four-step procedure that finds I prime by considering all positive and all negative cash flows separately using FW and PW equivalence relations. See your textbook for the details of this manual solution. Alternatively, the MIRR spreadsheet function displays I prime directly using the same procedure. The format shown here operates on the cash flow series entered into contiguous cells. Here's an example of a 3-year project for which multiple I star values are indicated. Using the external rate for reinvestment, 12%, and borrowing, 8.5%, the MIRR function results in an I prime of 9.39%. Now we will use this unique EROR value to make the economic decision. Since 9.39 is greater than 9%, though somewhat marginal, the project is justified. The second method, return on invested capital, ROIC method. This will result in yet a different I star value. We will call it I double prime. This technique is very useful for corporations that want to better understand how effectively the company uses its capital funds. Only the reinvestment rate, I sub R, is used to find the unique I double prime value. Again, there is a manual 3-step procedure available in your textbook. As shown here, it uses the future worth relation to move through the series 1 year at a time. In the final year, the F sub n relation is set equal to 0, and the I double prime value is determined. Unfortunately, there is no easy-to-apply spreadsheet function for the ROIC method. However, it is possible to develop a series of conditional if statements and utilize the goal-seek tool to find I double prime. Here's the same example solved by the ROIC approach with the reinvestment rate of 12%. Column D indicates the details of each future worth relation, and the goal-seek tool changes the ROR value until the final year's F value is exactly 0. In this case, cell 5 becomes 0 when the ROIC result is 10.55%, as shown in cell F8. As usual, the important closure to any such analysis is the economic decision. With I prime equal 10.55%, it is larger than the 9%, thus the project is justified. Now for a quick summary of what we have learned about all these rates of return. The internal rate of return is determined exclusively by the cash flow values themselves. However, there may be multiple of these I-star values in some series. The two external rates, I prime and I double prime, are based on reinvestment and are borrowing rates external to the project's cash flows. The I prime and I double prime rates are unique rates that can be used for a reliable economic decision, provided the external rate estimates themselves are reliable. It is vitally important that you always remember the following. All of these procedures can be bypassed if you perform a PW, FW, or AW analysis at a specified MARR. No multiple root problems are present with any of these techniques. That's it for the multiple ROR values. Thanks for watching.